Okay, ladies and gentlemen, if I could have your attention, please. My name is Gerhard Velitis. As President of the Astronomical Society of South Australia, I welcome you to tonight's meeting, a special meeting, a joint meeting with the Australian Institute of Physics and, of course, our Astronomical Society of South Australia, joint meeting presenting our speaker tonight. First things first, COVID safety is always an issue, even these days, while we might be behind it. If you feel uncomfortable about sitting next to somebody sneezing or whatever, feel free to move away. You're not rude in doing so and protecting your own health. And yeah, the other virus that's with us is phones, so please put your phone on silent or off, please. So the Braggs Lecture Theatre, emergency routes are basically the doors you came through at the back, or on your right, the doors here take you through to the exits as well. Toilets, the other important bit of information, they're also through the door on the right at the very back of the hall. So, yeah, toilets. So welcome to our monthly meeting. Our mission is to observe, understand, share and enjoy the wonders of the universe. Now, could I have a show of hands here of people who are visitors and not members of AIP or ASA? Broad terms. So, yeah, this is one or two of you. I've got a few words to say later about the benefits of joining our organisation. But for the time being, welcome. Also a show of hands from people associated with the AIP. Okay, there's a few of you there. Thank you for coming. The Astronomical Society of South Australia acknowledges and pays our respects to the Kaurna people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Kaurna people to country, and we respect and value their past, present and ongoing connection to the land, sky and cultural beliefs. So tonight's program, it's a short program, 4 dot points, but it's my pleasure first of all to welcome to the dais Dr. Darryl Jones, who is chair of the South Australian branch of the Australian Institute of Physics and is a senior lecturer at Flinders University in chemical physics. So ladies and gentlemen, please make welcome Darryl Jones, Dr. Darryl Jones.
Good evening, everybody. So my name's Darryl. I'm the chair of the South Australian branch of the Australian Institute of Physics. And as Gerhard said, I'm a senior lecturer at Flinders University. It's my great pleasure to welcome you all to the Braggs Lecture Theatre for tonight's public lecture, hosted jointly by the Australian Institute of Physics and the Astronomical Society of South Australia. This is an annual tradition that has existed since at least 1988, when Dr. John Davis gave a talk about the Sydney University Stellar Interferometer. So just a bit about the ARP. The ARP acts in many areas. We provide accreditation to Australian universities, ensuring the physics programs maintain high standards. We advocate on behalf of the community on matters relating to research, education, industry, and the physics community. We offer many annual awards for both students and researchers alike. And finally, we host many public events, including careers fairs, the Marie Curie lecture series, and other public lectures. And some of our upcoming events are shown here. So our next events are free careers nights and schools open day, presented in partnership with the Quantum Australia Conference, which is held here in Adelaide later this month. So please feel free to join in these events or share these with any other interested parties. And so now I would like to introduce tonight's speaker, Charles H. Lineweaver. Charles is an honorary associate professor at the Australian National University's Research School of Astronomy and Astrophysics. He has taught astronomy, planetary science, and astrobiology for more than 20 years. His research areas include exoplanetology, the statistical analysis of exoplanets and their habitability, cosmobiology, using our knowledge of cosmology to constrain life in the universe, and cancer, a new atavistic model. He recently completed an online video course, Are We Alone? Well, how did we get here? Dr. Lineweaver earned a BA in history from the State University of New York at Binghamton, an MA in English from Brown University, a BS in physics from Ludwig Maximilian University in Munich, and a PhD in physics at the University of California, Berkeley, where he was supervised by George Smoot, the 2006 Nobel Prize in Physics recipient. So it's now my pleasure to introduce Charlie to give his presentation. What is astronomy for and why is it important?
Okay. Thank you. Thank you, Daryl. Can you hear me up there in the back? Okay, good. I'm going to try to run this from the other side, and so I can look at the screen the same way you guys do. Actually, I'm not sure I can do that. Okay, so just look at those stars, Becky. There must be hundreds of them. That's Carl Sagan as a child. So tonight I'll be talking about why is astronomy important? And I will also at the end talk about even for AIs and aliens. I added that at the just because I thought it would be interesting that everybody seems to be worried about AI and taking over, and whether when we have a post-human future, whether we should still worry about whether we're alone or not, and whether astronomy will still be important to us. So now, I don't know about many of you, but when I was, 15, 20, 25, I had what's called an identity crisis. I think it's a common thing among human beings. And so you want to know, who am I? Where did we come from? And well, when I was, I guess, at first year in university, I read this book, The Cosmic Connection by Carl Sagan. And in 1973, it came out. And that's something that got me very interested in the connection between me and the rest of humanity and the rest of the universe. And that's what The Cosmic Connection is about. I can recommend it. It's still in print. And from this book, you'll learn, among other things, that we are the dust of long dead stars. Every atom of oxygen and nitrogen that we are breathing, every atom of iron and carbon in our blood was created inside stars before the Earth was born. So you're made mostly out of water. That's H and O. That O was produced inside stars that lived and died before the sun and before the Earth formed. Remember, that's 4.5 billion years ago for the sun and Earth. So we are nuclear waste. But that's not true of hydrogen. Hydrogen was made from protons and electrons when they first came together about 380,000 years, not million, but 1,000 years after the Big Bang, when the universe, which was cooling down, was cool enough so that the electrons and the protons could then form hydrogen for the first time. And then you have what's called the photosphere of the universe. And it's called the photosphere of the universe because earlier times, the universe was opaque. It's like a wall of plasma-free charges of electrons and protons. But when they came together to form hydrogen, the universe became transparent for the first time. Light was able to propagate to us. And that's what we see when we look at the cosmic microwave background radiation. And that's what I did my PhD in under George Smoot at Berkeley. So this is a picture, Apollo 8, 24th of December, 1968. It was the first color photo of Earth taken from deep space. And the guy who took it, William Anders, said, we set out to explore the moon, and instead we discovered the Earth. And this is more or less the theme of the talk I want to give tonight, because when you set out to explore beyond the Earth, you end up finding out much more about the Earth. And that's what I think he was trying to say there. So, in other words, the exploration of the universe is the discovery of who we are and how we got here. I like that so much, I'm going to repeat it. The exploration of the universe is the discovery of who we are and how we got here. The topic here is, why is astronomy important? And so a lot of people think of astronomy as about things out there. But what I'm making the point is, when we find out more about what's there, we're finding out more about who we are and what we are. So, for example, when we find out more about Mars and about Venus, we will there find out more about the Earth, how the Earth got to be the way it is. So another example. So For most of our existence as humans, when we looked up at the dark night sky, all those points of light were the distant campfires of our ancestors. We saw heroes, gods, and mythological beasts. There they are, mythological beasts. There's Antares and Scorpio. There's Hercules, Cephas, Cassiopeia. So all human cultures have painted their stories onto the night sky, and when something is that universal, there must be an adaptive reason for it. My dad was a high school biology teacher, so I grew up with Darwinism. So adaptive reason means it's important for survival. So again, I'm making the point that finding these things out and doing these things are adaptive and have helped us survive. The reason I'm mentioning this is because some people say, oh, you're wasting your time going to Mars or going to the moon or going elsewhere and exploring because we have enough problems back here. And I think those are not mutually exclusive sets. I think by exploring, you do a better job of taking care of your home. And that's the point I want to make. So a long time ago, we used to wonder, I mean, you can imagine somebody pre-science, they said, what makes the sun move across the sky? Why does that sun go across the sky? Well, the Greeks had Helios, and here Helios is being drawn by four horses with wings, and Helios is the god of the sun. He's being pulled across the sky. That's what happens. That's why it happens. And here's another picture of him. Now, the Egyptians had the sun god Ra, and he would sit on his boat, and the boat would sail across the sky. And that's why the sun went across the sky. And in the evening, when Ra sinks below the western horizon, how does he find his way back to the eastern horizon? If he comes up over there and sails across the sky, how does he get from over there to there in the morning? That's a simple question that I think we no longer ask ourselves, but you can well imagine that if you didn't know that the Earth rotated or anything else about the solar system, you would ask that question and that would maybe bother you. Well, it bothered the Egyptians and they came up with an answer. And that relies on Nut. Nut is a sky god. You can see there she is, the dome of the sky covered with stars. And what she does, when the sun goes down, she eats the sun, and then she swallows it, and then it goes through her intestines all the way down to her butt there, and then it gets back on the boat, and the boat travels around. And I don't have a laser pointer, so I can't point. Anyway, she eats it there, goes around there, comes out again, and goes across the sky. Actually, sometimes it has to go underneath her gastrointestinal tract is underneath the Earth. In any case, starting about 600 BC, there's Thales of Miletus. And there's Miletus, which shows you where it is. Thales broke with mythology and tried to explain the world, the universe, with theories and hypotheses that didn't involve gods. Now, I put the word and then I said universe. Now, the story of us finding out more about the world is us finding out more about what the world is, how big it is. And I don't know if the word universe was used by the Greeks, but the point is that our universe has gotten bigger and bigger and bigger. And I'll talk a little bit about how it gets big. But in any case, 600 BC, in the Greek world, they started to use some hypotheses rather than how the gods did it. So here's Anaxander of Miletus thought that the sun, moon, and planets were holes in an invisible wheel surrounding the Earth. Through the holes, humans could see the concealed fire behind it. And Pythagoras thought that 10 is a perfect number, thus there must be 10 heavenly bodies. These are the 7 on the days of the week, but then he added the Earth, the anti-Earth, and the invisible central fire. So he made up this idea of we need a counter-Earth, and we have an invisible central fire. I think you could call that model the cryptopyrocentrism of 550 BC or so. So that's Pythagoras. And then there's Anaxagoras. He was born in Clazomene. And there's the Peloponnesus in the oval. And he said the sun is a fiery rock larger than the Peloponnesus. So you can see these guys are trying to figure out what the world is around them. He also said if the heavenly bodies should be loosened by some slip or shake, one of them might be torn away and might plunge and fall to earth. So here's Metrodorus of Chios, 5th century. We're going through about 200 years of Greek philosophers here. He said, the stars are formed from day to day by the moisture in the air under the heat of the sun. So some of these ideas seem to us kind of like, what in the world are they talking about? And so we've made some progress. And I think in maybe 2,000 years from now, maybe only a couple of hundred years from now, they will look at us and say, wow, did those guys have some crazy ideas about the universe? Some of those crazy ideas I'll be talking about in a couple more slides. Oh, by the way, you can interrupt me at any time and call out loudly and say, hey, what about this or what about that? I like being interrupted because I like to interrupt people. Okay, so here's the geocentric model on the left, and this is Aristotle. He said, if there were more than one world, the elements of earth and fire would have more than one natural place towards which to move. So you can see that things, see that has a natural place in which to move towards the center of the earth. And if there were more than one place, that wouldn't make any sense because which way would it fall? That was his logic back then in about 350 BC. And so here's George Gamow's version of why you shouldn't explore the earth. You'd fall off. And then people wondered what makes the stars go round in the sky. Well, there's one model. The angels are see how they're cranking the sky around. And well, this is a kind of a medieval drawing that has been colorized. And the point is, we are very curious as human beings to try to figure out what lies beyond the horizon. How far can we see and what lies beyond the farthest we can see? And that's what I do as a cosmologist. And so the modern version of this plot is this thing here. So as you can see here, there's an eye in the center, that's us. And when we look into the distance, we see the photosphere of the universe. And the photosphere of the universe is like the photosphere of the sun. It was so hot, remember it was a hot Big Bang. It was so hot that you had electrons and protons separated, and therefore you had a wall of plasma through which light could not travel. The same reason you cannot see inside the sun. You ever try seeing inside the sun? You cannot. You look at the surface of it, the photosphere from which light comes. Beyond that is ions, and the light doesn't travel through. And so we have a photosphere of the universe, and I will show you, I'll talk about that. And then here's something interesting. Neutrinos, you may have heard of neutrinos. Neutrinos can go through the Earth like that, there's no problem. And but in the early universe, that means you could see, if you had a neutrinos telescope as good as we have for the microwave background, you could see much, much further. And as a matter of fact, you can see back to 10 to the minus 6, a microsecond after the Big Bang. Notice that the time of the photosphere of the universe, when the universe was 1,000 Kelvin, it was about 380,000 or 400,000 years after the Big Bang. Now,
what's the Big Bang?
What's the Big Bang?
When?
Oh, when is the Big Bang? Big Bang 13.8 billion years ago. And that's, we have ways of estimating the age of the universe based on general relativity. If you plug into the equations of general relativity, the expansion of the universe and what the universe is made of, it out pops an age. And that age currently is about 13.8 billion years. Actually, it's like 13.79 plus or minus point. I don't like to remember too much of the uncertainty because they're always changing the uncertainty. Basically, 13.8. If you want to round off, 14. In any case, the universe has a finite age, something my father hated. He said, you can't have a beginning of time. That makes no sense at all. But you say it enough times and you get used to it. The universe had a finite age. That's very important because as you look far away, you're looking to earlier times. A telescope is a time machine. So when you look at the moon, you're not seeing as it is now, you're seeing it as it was 1 second ago. When you look at the sun, you're not seeing it as it is now, you're looking at it as it was 8 minutes and 23 seconds ago. When you're looking at Alpha Centauri, you're looking 4 years into the past. And when you're looking at the photosphere of the universe, you're looking 13.8 billion years into the past. So that's our observable universe. Notice that the observable universe is different from the entire universe. Right? What we can see is a very small portion because the age of the universe is 13.8. Light has been traveling from these distant regions for 13.8 billion years, not for 15 billion years, not for a billion years, but only 13.8. That means it's a finite distance we can see. So let's look a little bit about what this photosphere of the universe. This is a map we made in the COBE DMR, the Cosmic Background Explorer differential microwave radiometer. We made this map in 1992. I did my PhD in 1994, and this is a map we made. The red is the galaxy, and this map is a full sky map. So you take it and take this map and wrap it around your head, and so it covers the whole 4 pi or 40,000 square degrees of the entire sky. There's a full sky map, and that's the galactic plane there. And as a matter of fact, the point on the far left and the point on the far right are the same point. That's why you have to wrap it around like that. The full sky, and when you look at the sky, now the dark spots there and the bright spots outside of the galactic plane are hot spots and cool spots in the microwave background. These are the fluctuations in the cosmic microwave background that people have been looking for decades, and we were the first ones to find it. Stephen Hawking called this discovery the greatest discovery of the century, if not of all time. And we are always proud of having a good compliment from Stephen Hawking. Now, so to get an idea of what this is a kind of counterintuitive. Imagine everybody in this room, there's a flat field, and everybody in the room has a clock, and we're going to all start screaming at noon. We're going to scream, ah, like that. And this field is infinite, okay? An infinite field of screaming people all screaming, and then they're all going to stop at the same time, okay? Now the question is, what are you going to hear? You're in some particular spot. What will you hear? Well, sound travels at about 330 meters a second. After about a second, everybody within 330 meters will be quiet, but everybody beyond that, you will still hear them screaming, right? Because their sound, they stopped, but their sound their screamings is coming to you. After about 3 seconds, everybody within a kilometer will have shut up, but everybody beyond that, you will still hear them screaming, right? You following this logic? Anybody not like this? And so you know where I'm going with this. Now replace the sound, the screaming, with photons. Replace the infinite field with really, really hot plasma of electrons and protons. And then the stopping screaming is when the electrons and the protons come together to form hydrogen. They stop screaming, and then you see the hotness, the screaming, recede from you at the speed of light. Just like that surface of last screaming is receding from you at the speed of sound. So that's what that picture I showed you, that discovery of the fluctuations, that is a map of this surface of the photosphere of the universe that's receding at the speed of light. Just like this surface of last screaming is receding at the speed of sound. Any questions about this? Say again? Yeah, what causes the perturbation? The answer to that seems to be quantum fluctuations in the early universe. So quantum fluctuations, you cannot get rid of them. Heisenberg uncertainty principle, you cannot get rid of quantum fluctuations. And so these, we think, were on all scales. As a matter of fact, the reason Stephen Hawking said this is the greatest discovery of the century, if not of all time, was because we saw a flat power spectrum. And the flat power spectrum meant that at large scales, we saw objects who were coherent on scales that were beyond causality. Why do we say that? Because, you know what, I'll get to this. I don't want to get it gets a little complicated, but the answer to your question is quantum fluctuation. I don't want to get into too much of the details. Anyways, here's 1992, me on the left with George, and here he is getting the Nobel Prize in 2006. And George just recently died, and you will see on the archive, remembering George Smoot, a lot of us, maybe about 20 or 30 of us, got together and wrote our memories of George. He died at the age of 80 in October. So there's the observable universe. And remember, it's a small piece of what looks like is an infinite universe. And we say it's infinite because when we measure, I don't know if you know this, but you know, you were taught in high school that the inside angles of a triangle have 180 degrees. You were taught that, right? And well, if you put that triangle on a sphere, that's no longer the case. The addition of the three angles is more than 180 degrees. And if you put that triangle on a saddle shape, then the sum of those angles is less than 180 degrees. And this simple this geometric topological fact is one of the ways we figure out what the shape of the universe is, the topology of the universe. And as far as we can tell, this universe is spatially flat, which suggests that it's spatially infinite or very, 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 very large. In other words, if we're on the surface, if this universe is curved and closed, then it's so big that we can't tell the difference between that and flat. It's like having a giant balloon that's so big, you say, oh, this is not a balloon, this is a, it's like the Earth. The Earth, people think, hey, it's flat, but it's a sphere. Okay, so the photosphere from this CMB, the cosmic microwave background, I put it there, and that's the photosphere of the universe. Now, just for perspective, most people who do astronomy study galaxies. This is a DESI survey, the best current survey of the universe, and all those dots are galaxies. And that's about where that red circle is in the very center. So you can see that the photosphere of the universe is much, much further. It's a redshift of 1,000. These galaxies in the DESI survey go up to 1 or 2 or 3 or 4, while the photosphere of the universe is a redshift of 1,000. So now on the left-hand side, you'll see the Kobe map from 1992, the W map from 2003, and then the Planck map from 2013. And so the angular resolution of the map of the microwave background has gotten much, much better. And remember, this is the photosphere of the universe, and then the DESI galaxy survey is right there, and then over here are computer simulations of what we think the universe is. It looks like if you could just see the dark matter. DESI is only the galaxies that are giving off light. Okay, so we found out a wonderful thing from the CMB. We found out that the universe is mostly made out of nothing, out of vacuum energy and dark matter in the brown, and then about 5% of normal matter. The sun, there's what the sun is made of, hydrogen, helium mostly, 2% other elements, and then life, you, trees, bacteria, are made out of hydrogen, oxygen, carbon, nitrogen. But we've done a little bit better. We've improved these numbers, and now we have about 4.4% of the universe is normal matter, and then about 1.4 of the sun is not hydrogen, helium. And then we have Chan-Sp, which is something like 98% of the elemental compositions of what life is made of. We're making progress. Now, I did want to show you this. This is a picture of a bunch of objects. And a couple of years ago, we had the idea, hey, let's plot all the objects in the universe on a single plot. So that we have electrons and we have fleas, we have black holes, we have galaxies, clusters of galaxies, we have bacteria, quarks. Well, let's put them all on a plot. And when we did that, here it is. And so the size is on the x-axis, and you can see they're, I don't know, 80 orders of magnitude in size. This is a logarithmic plot. It's a log-log plot. And then the mass is on the left. And you can see black holes. There's a black line there. And then the Compton limit is here. And it's too complicated to explain what these are, but go have a read of the paper here, Lineweaver and Patel. I guess I just wanted to brag about this and show you that we're making progress in trying to understand the universe, particularly about this point over here called the instanton, where essentially it's a black hole. It's the smallest black hole you can have, but it's also the most energetic gamma ray you can have. All the photons in the universe are right on that plot. You can see the electrons and neutrinos and neutrons and protons, and all on the Compton limit. And then you get to higher and higher energies, and you get up to an instanton, and that's where you come. Yeah, that's when your gamma ray has so much energy that it becomes a black hole. That's what's called an instanton. Please have a read of that if you're interested. So I thought I'd talk a little bit about the Hubble tension. The Hubble, the Hubble constant is a measure of how the speed at which the universe is expanding, and 70 kilometers per second per megaparsec. And the Riese result, now Riese won 1/4 of the Nobel Prize with Brian Schmidt and Sol Perlmutter for discovering the acceleration of the universe. And Adam Riese is now into the business of measuring Hubble constant, and they get something like 73 with an error bar like that. Planck, the CMB, the best recent cosmic microwave background, gives you a measurement of the Hubble constant of about 68 or so, with error bars that big, and you can see that they don't agree with each other. You see how the error bars don't overlap. Now, if the error bars on these two were, 5 times bigger, then they would be consistent, but they're not. The two groups are claiming that the error bars are that small. If we believe their claims, then they are inconsistent with each other and something is wrong. And that's what's called the Hubble tension. I should mention, however, that Wendy Friedman, using tip of the red giant branch techniques, has come up with a Hubble constant of about 70 with an error bar of about 1.5 or so. And you can see that that's somewhere in the middle. And she has been giving lectures about how the Hubble tension really isn't that tense, because she's probably right. She believes in her measurement, and you can see that that's somewhere in between. So somebody's making an underestimate of their systematic errors. And remember, in science, we have two types of error bars. We have random error bars and systematic error bars. To get an understanding, suppose there's a dartboard over there, and I'm throwing my darts over there, right? And I will see a scatter, and that scatter will be my random scatter, the random error. On the other hand, if there's a wind blowing in this direction, then all of my scatter will be pushed off to the side, and that will be a systematic error. Or maybe some of my darts are so heavy that I can't reach the... Anyway, there are all kinds of temperature or wind or something. Those would be systematic errors, and the random scatter is called the statistical error. And part of what you learn in science is you have to put those two together, and sometimes we add them in quadrature, even though they shouldn't be. But in any case, the Hubble tension seems to me as if it's not much of a tension, because I suspect, as is almost always the case, people who work very hard at getting an estimate don't spend 10 times as much effort in getting the error bar on that estimate, and they underestimate those error bars. So I don't think it's Hubble tension. I think it's the Hubble underestimation of systematic error bars of these groups. Now, to be fair, these groups are always looking for systematic errors, but I suspect they haven't found all of them. Now, so what I do when I do cosmological analyses, I just take this value. I do 70 plus or minus 2, and I try to keep everybody happy. Okay, now another thing that's come up recently is that this DESI survey, with this cosmological survey of the galaxies, has found that, hey, maybe this is evidence that the cosmological constant, this lambda, is decreasing. Now, I say maybe, it's suggestive, it's not very strong, but it's hinting that this constant that we thought is maybe decreasing. Now, I still suspect that that's wrong, but it looks like there's some evidence. We'll have to wait a couple more years to see if we have stronger and stronger evidence, or if we have weaker and weaker evidence. If we have weaker and weaker, we just can ignore it. But the point I'm trying to make here is we have a plot of the cosmological constant on the left-hand side. We think that during inflation or before inflation, we had a cosmological constant which was really, really, really high. This is the energy of the vacuum. Now, you probably are not all physicists, so you probably think that nothing means nothing. But if you're a physicist, you know that nothing means irreducible fluctuations coming into and out of existence that you cannot get rid of. And therefore, if you're a philosopher and you say the word nothing and you mean nothing, you're wrong. So everybody in this room probably has the idea of nothing. Nothing is with absence of everything. But we physicists have discovered that that's baloney. There's no such thing as this philosopher's nothing. There is the physicist's nothing, and you should live with it. You cannot get rid of this stuff. This is the definition of a vacuum. There's no matter, there's no sound, there's no light, but there is this irreducible fluctuations coming into and out of existence. That is the nature of nothing. And so when a physicist like Lawrence Krauss says the universe comes from nothing, the philosophers say, oh, that's impossible. You can't have something from nothing. But we physicists know that this nothing really is a lot of stuff. And the lambda I that is so high means it's really a lot of stuff. It's false vacuum. It has much, much, much more particles coming into and out of existence. And then what happens during inflation, we think this constant goes way, way down to the true vacuum, which we used to think might probably zero, but we found out recently, in 1998, that it's not. It has a constant value, we think. DESI says it might be decreasing, but smart money is still on. It's a constant. And it's a small constant, but it's still there. And that constant is what is making the expansion of the universe accelerate. Remember the difference between velocity and acceleration? The Hubble constant tells you the velocity. The lambda tells you the acceleration of that velocity, the change in the velocity. And that's what lambda does. Any questions about any of this so far? Right. So if you're in a boat on, I don't know, the Pacific Ocean, or you don't know what kind of ocean you're on, but you're on a boat and you just see horizon and there's nothing on the horizon. That is your observable universe. And the question is that the edge of the universe? And most people who are in a boat say, no, that's not the edge of the universe. That's just as far as I can see. Most scientists would agree with that statement. There's no such thing as the edge of the universe except for the arbitrary nature of us being here, the universe having a finite lifetime, therefore we can see only a finite distance. But that finite distance is epistemological rather than ontological. It's what we can see rather than something fundamental about the universe. If we were over here, this would be our observable universe. And if we're over here, this would, just like if you change your position of a boat, here's your horizon, go over here in a boat, go over here, then here's your horizon. It's a different place. Now, whether there's something interesting beyond somebody's horizon that says, hey, it's different over there, we don't know. But so far, smart money is on, it's all the same. Speak louder, please. Yes. The original size of the observable universe. Well, it's a little bit complicated, but the universe was expanding so much that let's put you here, okay? And let's say that there's something here shining towards you. The universe is expanding so rapidly that the light trying to go this way gets pulled away. It's like a swimmer in a current the current is faster than they can swim. So the light that's trying to get to you gets pulled away, and then the Hubble constant goes down, and then it's finally able to get to you. This is called a past light cone. And so I'm not sure whether that answers your question. Okay, all right. Okay, but these are very fundamental things about how do we understand our place in the universe. And well, here's a plot of that light cone I just told you about. See on the top panel? That's that light cone. It goes like that and it comes down. So the top light cone, the light is trying to get to you, it's getting pulled away, and then eventually goes like this. So when you're up here and you look into the past, you're seeing along that light cone. So when you see the most distant things possible, you're essentially seeing right next to you because of that effect. Now, the thing I wanted to point out with this is that you see these dotted lines? Those dotted lines are galaxies that are at rest. But you can see them moving away from the observer in the center simply because the universe is expanding. And so in the second panel, you can see that the expansion of the universe has been taken out so that those galaxies, distant galaxies, are moving straight up and down. The reason I'm showing you this is because due to lambda, due to this cosmological constant, due to the acceleration of the universe, those objects at redshift 10, redshift 3, redshift 1, increasingly our event horizon is getting narrower, 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 and getting smaller. What that means is that the objects that we can currently see, these distant galaxies, are getting redshifted and will redshift out of our ability to see them. Much like if we drop a star or a person into a black hole. They will get redshifted, and they'll be there forever, redshifted. But if you all could look at them in optical and then infrared and then microwave and then radio, you could always see them as long as you could shift your observability to the redshift of the object. Now that's the same thing that's going to happen to our universe. So the optical astronomers are not in for a good time, but the radio astronomers can look a lot longer because optical light will get so redshifted that it goes into the radio. And then they'll want bigger radio telescopes to see even further. And essentially, they'll never go out. When an object falls into a black hole, it never disappears into the black hole. It's always frozen on the surface. That's the same thing that will happen to all of the galaxies in the universe beyond the local group. Andromeda and us, M31 and us, we're going to go like this, come slide, and we will have an island universe surrounded by an event horizon of these extremely redshifted everything that only radio astronomers and probably them, they won't be able to see them anymore either. Everything will get redshifted out of existence. And that's what's called the formation of island universes. So, do we live in a multiverse? This is a question you may have come across. And here's a picture of it. Now, the way you're to understand this is that lambda I in the middle, that's the red stuff. That's the stuff with lots and lots and lots of virtual particles coming into and out of existence, lots of energy in the vacuum. We call it the false vacuum. It has lots and lots of stuff in it, even more stuff than our vacuum. But then what happens, presumably, is out of this extremely energetic lambda, you get a condensation of a bubble in which the lambda goes way, way down. And you go from false vacuum to what we now call true vacuum. And our universe could be one of these bubbles that has condensed out of this very, very, very energetic background, but it's very cold because it has been, it's accelerating very, very rapidly because lambda sub I stands for inflation, is really accelerating the expansion by enormous amount. And so the idea of internal inflation is that pop, 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 everywhere in this red background, you get universes popping into existence. They get populated by energy. The energy then produces matter and antimatter in almost equal amounts, and then they annihilate, and then we're left over with the matter we see around us today, a matter-dominated universe. The question about whether in these other circles, these other bubbles, you will have the same baryon asymmetry, where you have the same, you have like one extra part. There's a billion antimatter particles and 1,000,000,001 matter particles that come together, annihilate, and then one matter particle is left over. That's what you and I and everything in the universe is made of. That extra 1/100000th of the amount of matter we had earlier. Now, the question that a lot of scientists say is, well, was there a choice? Did the universe have a choice in that baryon asymmetry? Could it have been 2 parts in 1,000,000,000 rather than 1 part? Or could it have been exactly equal? If it were exactly equal, then we wouldn't be here. There would be no matter. The universe would just be filled with photons, and then it would just dissipate. You wouldn't have any baryons. You wouldn't have any atoms. On the other hand, maybe in some universes you get more antimatter. And then they think, oh, look, our universe is made out of antimatter. How is that? Why is that? You have a question? Lambda. Lambda is a Greek letter. It stands in for the amount of energy in the vacuum. And that is what when they got the Nobel Prize in, 2015 for the discovery of the acceleration of the universe. And if you see the expansion of the universe accelerating, this is the term that you put into general relativity to explain that. This is the term in general relativity that takes that into consideration. This is the simplest way to understand the acceleration of the universe, and it has a particular value, which we now know what it is. Lambda sub I is the energy in the vacuum that was before inflation. It was much, much, much higher, and therefore the acceleration of the universe was much larger, but that energy that was purely in the vacuum gets dumped into one of these bubbles as it condenses, and that's what produces all of the matter in the universe. Sad. I'm sorry, I don't deal with emotions like that. I'm a scientist. I don't think any facts are said. How about human death? Maybe people think that's sad. I'm working on that one, whether that's sad or not. I do not know. So no, I don't even understand. What is sad? You think if it came back together, it would be less sad? So then you'd be burned to death. That's happy for you? That's a crazy idea. I don't want to even go there. I don't want to. Actually, Stephen Hawking and some of his colleagues like to do that. They like to say, oh, our universe goes here, and then it gets smaller again. And so they like to they'd like to say, well, there's a problem with the entropy in that model. And entropy of the second law says that entropy will always increase. And so people used to think, Stephen Hawking used to think that if the universe is expanding, that's what making the entropy of the universe increase. That's what's responsible for the second law. But then he said, well, wait a minute. Then it's collapsing. That means the entropy has to decrease. And that's impossible, and that doesn't work. And so he said, yeah, that's a bad idea. He threw it out. Penrose, I think, convinced him of that. So no, that's not a great idea at all to recombine, to recollapse. Terribly sad to do that. That's even worse. That's even sadder than what the reality is. Do we live in a multiverse? I think the answer is yes. And but what kind of multiverse? And so for the last few minutes, I'll talk about what kind of multiverse. So here's a picture of, you got a kangaroo here, and each of those kangaroos has an observable universe. And photons are coming from over here, and photons are coming from over here, and that's the size of one of the observable universes. Then you move over, and then you have another observable universe, et cetera. So in a spatially infinite universe, you have an infinite number of independent observable universes, simply because you had a t equals 0 Big Bang, and it's now about 13.8 billion years after the Big Bang. So you have a finite size light cone. So this model of having this red that has a much, much higher vacuum value, a lambda sub I, and then you have this condensations into lambda. Now, it's not obvious. A lot of people think, hey, this lambda could be different from the lambda over there, and every condensed bubble could have a lambda, a different one. And so then you say, well, what's the mother distribution from which these lambdas were chosen? And a lot of very clever mathematical physicists say, oh, I'll just guess. But I don't like to do that. I don't like to guess when there's no evidence that there is a mother distribution. So I just say, well, maybe it's all the same. And people say, well, maybe the speed of light in each one of these condensed bubbles is different than the one in our bubble. Maybe the gravity, the constant g, the strength of gravity is different. Maybe the ratio of the mass of the proton to the mass of the electron is not 2,000 like it's in our universe, but maybe it's, I don't know, 2. And then with all of these imaginary distributions, they say, oh, but only in a small part of these distributions is compatible with life. Now, that's what's called the fine-tuning argument. And I am one of the people who say, oh, that's baloney. Why do you imagine that there are these mother distributions? Because there's no evidence whatsoever for these mother distributions out of which you are randomly picking these values that you are then assigning to these independent condensing bubbles. Any questions? So go ahead, loudly, please. Yes, basic question. Yes, that happens all the time. At high enough energy, matter of fact, in the early part of the universe, there is so much energy around. You had a photon, it splits into a proton and antiproton. They come together for a photon, and then they just go on and on and on, back and forth and back and forth. And there's conversion going on all the time. As soon as the universe cools down so that the photons no longer have enough twice the mc squared to make a positron and an electron, for example, then it just sits there and it doesn't produce those particles. Now, when the energy is much, much higher, you produce more and more particles. And you go all the way up this, maybe an infinite cascade into higher and higher mass particles that you're producing them and then they're decaying, producing them and decaying. And so that's really an exchange that goes on very much in the early universe. But there, you're not talking about fusion. You know, fusion in the sun is about 0.7% efficient. The mass of, the hydrogens and the deuterium gets converted into helium, and then the difference in those masses gets turned into energy, but that's only like 0.7%. When you have matter and antimatter, that's 100% efficient. So in the early universe, you had 100% efficient conversion between energy and matter all the time. And we turn up the knob as you get earlier and earlier, it gets higher and higher and higher energies. But we can only turn up the knob so much in our particle accelerators, and so we don't know what's beyond the energy of the LHC in Geneva, for example. That's why it's so important to turn up that knob to get higher and higher energies, because then you can discover, oh, we got a new particle that comes into existence here. Oh, we got 2 more, et cetera. Does that answer your question? Okay. Now, condensation. So help you to visualize the condensation. I have put this little picture of a spider web with water vapor that has condensed out into the drops that now ornament this lovely spider web. And so that's an analogy where the water vapor in the background is analogous to the lambda sub I, which is the high amount of energy in the vacuum. Interesting thing about this energy in the vacuum, you cannot have a speed with respect to it. Now, I showed you those maps of the cosmic microwave background. One of the things we had to remove was the dipole. The dipole is because we, the Earth, the Sun, our galaxy, is moving through this background radiation. And in the front of us, it's hot, and behind us is cool. That's just redshift due to our velocity. That's just a standard Doppler shift. Now, why do I want to mention that? I know. Because lambda, if the universe is not filled with microwave photons or matter, if it's just filled with this lambda stuff, the vacuum, you cannot have a velocity with respect to it. It's Lorentz invariant is a fancy term for that. That means if you're in a universe that's just lambda, just has vacuum energy, you don't know whether you're going like this or going like this. You can't have a velocity with respect to it. It's really interesting stuff that way. It's called Lorentz invariant. Anyway, inflating background. Is that clear about this inflating background? This is, well, let me go on. Oh, yes, yes. Yes, yes. That's right. Actually, I'd say the expansion of space, not the expansion of space-time. So now, people who study the origin of the universe, you know, the density goes up, you get closer and closer to the Big Bang, the temperature goes up, and then you have so much matter in such small scales that you have gravitational fluctuations that you have to use quantum mechanics to talk about. So you have to do quantum cosmology. And the point I want to make about that is that once you start doing quantum anything, you're no longer talking about a single event. You're talking statistics, multiple examples. And that sentence that I just said is one of the reasons why most physicists believe in the multiverse. Because in order to understand the origin of our universe, we have to apply quantum mechanics to the Big Bang. And once you do that, you get what this picture here. This nothing that is not really nothing is what gives birth to all these universes. Some of them are, you know, just go boop, boop, and go out of existence. Others are green. Maybe ours is the green one. Maybe they have different values of lambda. I do not know. I don't think anybody knows. But I guess I just wanted to make the point that the reason why most physicists believe in a multiverse is because they know that to understand the origin of our universe, you have to invoke quantum mechanics, and nobody invokes quantum mechanics without invoking statistics. Multiple universes. One thing here, you know, I talked about condensation here, but other maps, you might have seen this map, this diagram of the universe, and notice that these bubbles are connected. And that's different from just condensing here and here and here. And notice right over here is a blow up of that blue bubble there. And in this blow up, it looks kind of flat. And there in the pink is our observable universe. Now, because the universe is accelerating, that observable universe is getting smaller and smaller and smaller. And so, as I said, we're going to have the local group island universe to deal with. And that's has interesting implications for what it means to be, are we alone? So, for example, suppose that there's aliens over here, but there's aliens in this galaxy and not that one. Well, the galaxies that are inside our observable universe are being redshifted out. And if they're an advanced civilization that's going to come and kill us, we don't need to worry about them anymore because they're getting pushed out of our observable universe. Here's another picture of eternal inflation. Everything's connected here. I think the idea here is that if you have a universe and you have a black hole, then that black hole is in some sense the entrance to another universe. And so if you've read this book, I can recommend it, Black Holes, The Key to Understanding the Universe. And this plot over here right here is our universe right there. And there's inside the black hole, and there's another universe, and there's another. So there's all kinds of universes inside black holes. And that's different from the type of multiverses I've been talking about, which are condensing out of the vacuum. That is using black holes as an entranceway to other universes. And that might also be true. So that's another version of the multiverse, that every black hole, the space inside of a black hole, you may have heard, is not part of the space-time of our universe. And that's because it's another universe. And inside that black hole, maybe there's another, I don't know. Anyway, this is very speculative, but I do agree with Brian Fox and Jeff Forshaw, who say this is the key to understanding the universe, at least the black hole part of the universe. Now, are we alone in the universe? Well, you could say, are you, Charlie, you mean, are we alone in our island, or alone in the whole universe, alone in the entire, or just the observable universe? Anyway, I've talked about various versions of the universe. And so if you hear somebody say, well, are we alone in the universe? You say, which universe are you talking about? So hello aliens. We haven't found any yet, despite what some of the American press say recently. We have not found aliens. So we can ask the question, are we alone in the multiverse? That's a slightly different question, isn't it? As a matter of fact, we have 3 different questions about are we alone right here. We have inside the pink here, that's our universe. And we can ask, are we alone in our observable universe? Or are we alone in that blue bubble? Or are we alone in this infinite, eternal concoction tree of universes? So there are 3 different questions depending on what you mean by universe. As a matter of fact, there's a 4th one, because you see in the very center there, that would be the only thing left in our island universe. And so presumably we're much more interested in whether we're alone in our galaxy and Andromeda, because we're going to come together, we're going to know each other for a very, very long time, when all the other galaxies are going to disappear. And so we don't need to know about them. If there's some kind of terminators living in those other galaxies, they will, if they don't find us soon, it's going to be too late for them. So I wanted to finish on Pizarro. Here's Pizarro, November 16th, 1532, with 150 Spaniards conquering the Inca Empire, Atahualpa. And I guess I'm showing you this because Stephen Hawking said the history of advanced races meeting more primitive people on this planet is not very happy, and they were the same species. I think we should keep our heads down. Now the reason why this makes sense is because I wrote a paper about the age distribution of Earths in the universe, and the average age of an Earth-like planet in the universe, is about 2 billion years older than our Earth. Now, if there are any biologists in the audience, you know that 2 billion years ago, we were probably some kind of barely an amoeba. So you can ask yourself, how much empathy or sympathy or care do you have for amoebas? And that might be the best ethical projection you can have of what the aliens will think of us on average. And that's why Stephen Hawking said, we should keep our heads down. So it's better to discover than be discovered. And he also said, I don't think the human race will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet. And here is H.G. Wells, who said, human history becomes more and more a race between education and catastrophe. I think you can see that going on in the US right now. So AI takes over. Let's suppose that AI controls the universe. The internet turns into the AI brain, and then it says to itself, am I alone or are we alone? And it's still a valid question. I mean, we have a pre-human past, and humans are about 300,000 years old. And presumably we will have a post-human future, and it might look something like this. And in our post-human future, the question, are we alone, will still be an important one. Because you can imagine AI taking over the Earth and the solar system, it still will be left to the question, hey, are there other AIs out there that are going to come destroy me? Just like we have some of these fears. And so it too will say it's better to discover than be discovered. So this question of discovery in astronomy is so important that even AI will have it as an explicit question that it will need to answer. And so it too will invest lots of money in exploring space telescopes. And anyway, now that's AI. What about aliens? I think aliens too need to keep their heads down until they colonize the entire island universe. So, we always think about aliens, they're going to take us over. Like I said, they're 2 billion years more advanced, if you believe that. And so, but let's suppose that there's some aliens that are 2 billion years more advanced. They come and kill us all and then take over. But they have to look over their shoulders because they're not the only ones in this universe. If we have technology and they have technology, there's going to be technologies everywhere. And so you're always going to have to be looking over your shoulder for more advanced technologies coming and not caring about you. So even the aliens have to worry. Even the aliens, after they kill us all, will have to worry about these questions. Are we alone? And they will put money into astronomy. It's so important that even the aliens and the AI would invest in it. So I guess the conclusion is on the largest scales, we'll always be lost. Now, I guess I'll almost finish here. Steven Weinberg, somebody I like very much, he wrote in the last part of First 3 Minutes, a book he wrote about more than 30 years ago. The more the universe seems comprehensible, the more it seems pointless. So here's an illustration of that. We found out that we weren't the center. Copernicus found out that, we're not the center. And then what happened? Then Darwin said, oh, we're just another animal. We're not any special in God's vision of image. And then Freud said, you don't even know what you're thinking about. And then materialist reductionists said, oh, you have no free will. You don't have any agency. And then we find out our star is at some anonymous position in the boonies of the galaxy, and there are 100 billion other galaxies in the observable universe. So, and then here I am telling you, hey, it might be a multiverse in which you are even more anonymous. So the whole thing is pointless. It's a dethronement, humiliation, loss of hope. But you can reinterpret this, that look, we've made progress. We have increased understanding. We found out that the Earth is not in the center. Isn't that good of us? We found out that we have evolved on this planet with a result of 4 billion years of evolution. We found out that there are things inside our head that we don't know about that sometimes come out in our dreams. We found out that materialistic reductionism has something going for it, and maybe we aren't free as we think. And so what if we're on the boonies of a galaxy? And isn't the multiverse a wonderful idea? And, well, we don't know if it's true. It might be like some of those early Greek ideas, but it is one that we're trying to figure out whether it is true or not. And we have some evidence, and we're trying desperately to find out how our universe originated. And I think that's the end. I will show that this is a website I put together, that MOOC that you mentioned, arewealone.us. If you're interested more on are we alone? Well, how did we get there? Go to this website. And thank you very much.
Now, I'm sure there'll be a few questions around the place, and I'll pass this microphone to my faithful runner here in the middle of the crowd who can do the back of the hall. Okay, who's got a question? Hands up. We want to transfer the microphone to you because we're recording the session here, and therefore your questions will be heard on the recording, we hope.
You mentioned before a redshift on the microwave background.
Wait, where's the person? Raise your hand if you're talking.
All right.
Up there? Okay, yes. Go ahead.
You mentioned the dipole before, your redshift from our motion with respect to the microwave background.
Yes.
Does that mean it's possible to define a rest frame for the universe then?
Yes.
And does that
violate everything you learned about special relativity? Yes.
Yeah. Does that frame have to be the same for the CMB and for example, the neutrino sphere?
That's a good question. We don't know, but we'd love to test that. So what you have to do is get a neutrino detector that is sensitive enough to the neutrino background so you can see the dipole due to our velocity, which is about, the local group looks like it's moving at about 600 kilometers a second. So it's about 1 part in 1,000. So that's beta, V over C. Wow. Is that large? And so that's the, matter of fact, when we first discovered the microwave background, Penzias and Wilson discovered this. And then in about 1977 is when the dipole was discovered. And then 1992, we discovered the other fluctuations at about 100 times lower level. So yes, matter of fact, one of the questions that I like to ask my theoretical friends is, where did the rest frame of the universe come from? If the early part of the universe was just lambda, just vacuum energy, there is no rest frame. And then during what's called reheating, that false vacuum energy, the potential energy, gets dumped into a rest frame. And is there a choice? Is there a mother distribution of rest frames that is chosen when that happens? I do not know. I don't know anybody who does.
Yeah. Yeah, holds implications for conservation of momentum as well. Yeah.
That I don't understand, but
Yeah, no, well, no, it suggests, that the matter in the universe should, the velocities of matter in the universe should have an isotropic distribution around that rest frame, shouldn't they, to preserve conservation of momentum?
well, I'm happy with conserving momentum, but you can have with respect to which rest frame. I mean, let's suppose that I have one bubble over here, and I'm going to make it with respect to that bubble. Actually, it's hard to even talk about the space here because you cannot have, that white stuff here or the red stuff in the other diagram? I told you cannot have a velocity with respect to it. So that tells you, I think it tells you, that you cannot tell whether those bubbles that are universes with their own rest frames have velocity with respect to each other or not. Right? Because that would be moving through this stuff that cannot give you a velocity. It's a very profound stuff you're asking about here. And I don't know the answer, except for what I told you.
Try another one, but pass around first.
Please continue asking those questions in your spare time.
Sorry, just a question on opinion more than anything. Is there any reasonable likelihood that we'll be able to travel near the speed or past the speed of light?
It depends what you mean by we.
future?
We've already made protons go 99.9999% the speed of light, so yes. But you don't mean protons, you mean people?
Yep.
Well, I think not, because your mass would then increase by factors of 1,000 or 10,000 or so. I'm not sure what that would do to the human body. There are other ways to go fast, though, and that is if you can control the vacuum. If you can control lambda, if this stuff we talked about, the lambda sub I and lambda, if you can control that. Now, there's a minor way in which we can control this. You might have heard of the Casimir effect. You take two plates, conducting plates, and you put them very, very close together. What you're doing there is, if there are these fluctuations that are coming into and out of existence, when you put these two plates together, you are reducing the long Schrodinger wavelength particles that are coming into and out of existence. So you're changing the nature of the vacuum. So if you could change the nature of the vacuum on a big scale, such that, hey, I want to go this way, why don't you put some things to accelerate the universe here and contract it over here, then that would be one way to go faster than the speed of light. You're not going faster than the speed of light in your own reference frame, but compared to the other parts of the universe, you are. It's just like, you've heard of Hubble's law, V equals hd. Velocity of recession equals some constant h times the distance. If the distance gets large enough, then that velocity of recession is larger than the speed of light. So again, this is for somebody who likes special relativity. You can't go faster than the speed of light. Well, you can. And matter of fact, you have to in an expanding universe because of V equals hd. Just increase d and you get increase of velocity. And there is no restriction to the recession velocity because it's kind of a phony velocity because it's not velocity with respect to a rest frame. It's velocity with respect to some distant observer. And the space in between is expanding, and these things are staying still. It's like putting dots on a balloon, blowing up the balloon. The space between those dots, the dots are staying perfectly still in their own rest frame, but they're moving apart really, really fast because the balloon is expanding. The space between them is expanding. And so you can have recession velocities of that nature greater than the speed of light.
Thank you.
Any other questions? All right, somebody wants a second go there?
Yep.
Another question coming.
You talked a lot about the energy of the vacuum. Do you know what determines that energy? I mean, doesn't it come about from the energy time uncertainty principle?
It doesn't come about from the energy.
The energy time uncertainty principle, is it from that?
Well, the uncertainty principle has energy time, but they're also, position and momentum. So there are about 5 uncertainty principles, but the answer is yes, it comes about because of that. In other words, it's very, very closely related, but the easy way to think of it is, I guess there's no easy way to think of it. It's particles that come into and out of existence and you can't get rid of them. That's what I just say to myself enough, but it is related to the uncertainty principle. Well, let's talk about what you mentioned, delta E, delta T. So the uncertainty in the time times the uncertainty of the energy is greater than h bar, Planck's constant, right? So what that means is, if the uncertainty of E, I can borrow a large amount of delta T, delta E, if I only borrow it for a very, very short delta T. So I can create a giant particle for a very, very, very short time, or I can create a small particle for a long time. It's like borrowing money from a bank. They say, oh, if you borrow a lot of money, it's only for a little time. And that's the nature of what is fluctuating into and out of existence. Instead of reading it as delta E, delta T, you can say, you necessarily have a fluctuation in energy that necessarily has a corresponding fluctuation in the amount of time that it can exist, and then it has to go back out of existence. That's the one way to interpret the Heisenberg uncertainty delta E, delta T as these particles that are irreducible fluctuations in the background.
Right, if there's no further questions, I have only my own comments to make in terms of, we've heard some very succinct words about the relentless heat death of the universe as entropy always increases. But from time to time, entropy does work in the other direction. When sun shines on a grape, where is that bag?
Well, what he said is wrong because you can't
Some-
violate the second law. And we are all organized. We say life forms are violations of it, but it's not true at all. If you add up all the poop and all the CO2 that you've put out in your entire lifetime, it is far exceeds the low entropy that your body represents right now. But you would say.
But from time to time, sun shines on a grape and produces something worthwhile out of the entropy death of the universe. So, Charlie, next time you
Thank you.
consider the universe, have a glass of that.
I will.
And think about
Thank
all
you
of our
very much.
futures. Thank you, Charlie, for a great presentation. Ladies and gentlemen, please thank Charlie in the usual way.
Thank you. Oh. Ooh, yeah. Violating the second law. No. So I'll be here for a while. I'll be here for a while if you want to ask some more questions in private.
We have coffee afterwards at the back of the hall, so
Okay.
I'm sure Charlie's amenable to discussing the wonders of the universe a bit more up there where we came through. Right, thank you, Charlie. Now I'll move on. Oh, black holes, are we alone? Moving. Sorry, stepping through your. All right, we've had questions, thank you. Now, ASA has a YouTube channel, youtube.com/astronomy.sa, where hopefully you'll be able to see tonight's presentation as one of these recordings of a number of things on our YouTube channel, including the Sky this month and Colin Hill's education sessions when they work as recordings, and various past speakers as well, one of whom will be Charlie coming up. So look out for our YouTube channel, Astronomy SA. One of our more important videos on that channel is the Sky this month, and our Paul Martinotis does a bi-monthly review of what's up in the sky. It's probably for last month at this stage, with the month coming up shortly, but every month the sky turns 30 degrees, so compensate if you're looking at that video for information about what's up in the sky and the date involved. Now, a couple of other updates. We have a website and member database upgrade occurring for our members with a group called Member Jungle. They're an Australian-based association management organisation running web servers and space to host member databases and websites. So we're looking forward to a website that works for public information and internal member services. There'll be more information coming on this before too long, but particularly for members of ASA, you'll probably receive an email before too long asking to confirm all the details that were in the member database in a different format, and we will move forward with that new information. Our existing YouTube, Facebook, Zoom, and all the other aspects will continue, but so this is specific to our member database and website. Now, if I could bring Michael Mattiazzo up here, he's got a few words to say about progression of comets in our skies.
Thank you, Gerhard. Yeah, just an update on comet maps. This is the last image I took before it dipped into twilight. So this was on the 22nd of March using a C11 telescope. So what is MAPS C2026A1? It's a member of the Kreutz family of sun-grazing comets. So in 3 days' time, it's going to get to 0.005 astronomical units, or in kilometre terms, 820,000 k's from the sun, but actually 160,000 k from the surface of the sun. That's equivalent to 1.2 solar radii at 13 hours UT on the 4th of April. So the question is, how bright is it going to get? It's potentially could get as bright as Venus, or the big or, it could disintegrate. So imagine something, well, you'd probably disintegrate if you got to 1.2 solar radii. But it's still alive as of today. It's mag 6.5. It's currently visible in the punched and stereo A data. So we're keeping a close eye on it. But the next 3 days are quite critical. Now the MAPS was actually discovered by amateur astronomers. There was a collaboration of Maori, Attard, Parrott, and Signoret. So Kreutz, if you haven't heard of what a Kreutz sun grazer is, they've been responsible for quite a number of great comets in history. And I've promised Gerhard I'd give a talk in June as well about the Kreutz system. So definitely come over to have a look at that. And they usually have an orbital period of about 750 years. This one in particular, though, is quite odd. It's coming in with an unusually long orbital period, 1,740 years. So this is James Webb Space Telescope image of it. It might look good, but it's not very good because it's only indicated a nuclear diameter of 400 meters, which is quite small. We were hoping for something a bit bigger. Now, a comparison comet, if you did manage to get to see it, it was C2011 W3 Lovejoy, which we sort of suspected that was going to be about 500 to 700 meters, so similar size. Now Lovejoy did manage to pass through perihelion, but disintegrated several days later. But it still managed to put on a spectacular show, as you can see in this photo taken by fellow Tabur in Canberra. So Lovejoy ended up becoming the great headless Christmas comet. Very spectacular, had a naked eye tail 30 degrees long. But this occurred during a favourable time for the Kreutz system. So what can we expect of MAPS? So it's going to you can follow its passage through the Soho-Lascaux C3 coronagraph using that link, Soho-Nascom Theatre, choosing the C3 image at 1024 resolution for best results. Now I also use a solar monitor phone app. You can actually see you select the telescope on that, and you can actually catch up with the Soho-Lascaux C3. So that's quite easy to see. And it will enter the field of view on on the 2nd of April at 1800 UT. So that's around the Friday morning. So if you get up Friday morning, you can start looking at it. So Terry sent me this image, one of the last ground-based ones on the 27th of March. So I personally think it's got less than 50% survival chance, but just in case it does, don't expect it to be a great comet, but it might show a tail 10 degrees long, quite bright, spotted from the evening of April 7, very low on the western horizon, about after 30 minutes after sunset. Should be quite bright, standing out in the twilight, rising. The tail should be rising vertically. But keep an eye on my Southern Comets Facebook page, and I'll let you know how it turns out. Don't mistake it for Venus, which is a very bright object that's starting to rise in the west. So Venus will be 10 degrees to the north of west. So the comet will be directly west. And each subsequent night will offer a better view as it emerges out of twilight. But it'll fade rapidly and remain low. If all else fails and this disintegrates and we see nothing, we have another opportunity later in the month. It's C2025 R3 Pan-STARRS. That's currently only visible in the northern hemisphere, morning sky. I just captured this photo using a remote telescope in Utah the other morning. So it's currently MAG 7.0 and brightening very quickly. So this thing will get closest to the sun on the 19th of April at 0.5 AU, which is exactly halfway between Earth and Sun. And what's most interesting is that it will also be at closest to Earth around the same time, about a week later. So it's basically directly between Sun and Earth. And that should reach potentially MAG 1st to 2nd magnitude at its peak, but it will be too close to the Sun by then. But by the time it emerges out of twilight from the end of April, it might be 3rd, 4th magnitude. Ideally situated in the evening sky during May as well. And if MAPS survives, you'll see them both. So, but this has to survive perihelion as well, but it's much more likely to. So, any questions? No, all good, thanks.
Yep, as Michael said, Michael will be back in June to tell us all about these comets, either why they fizzed or why they were spectacular, but one way or the other, it'll be a very interesting review. So, other things coming up in ASA for our members, service award nominations and imaging awards open May the 1st. So keep your eyes open for more details there. May the 1st open and close June the 30th. One of the most important dates of the calendar is our annual dinner and awards night for the awards mentioned above. This year it's on a Friday, so please note it's a Friday, not a Saturday. Friday, 4th September, we got a much better deal for the restaurant facilities as a result. Activities and events for April. Usual Astro Imaging Special Interest Group Zoom meetings and ASA at home. 28th April and 10th of April respectively. Member viewing nights, Stockport, Saturday the 11th and 18th of April. Around New Moon, Tuparang also on the 11th of April. For the public, because those events are basically all for members, one of the member benefits we have at ASA, public viewing nights at Hawthorn Dean Oval will resume in October. And the next public star party is at Stockport, Saturday, 23rd of May. As we get closer to that, keep an eye on our website. Hopefully it'll be a new website by then, but one way or the other, same website, same address, news on our public activities. Now we have a heads up for Science Alive. We get very involved with Science Alive and bringing the good news of astronomy to kids and adults for over 2 to 3 days in August. So I'll ask Michael Chartres to say a few words about Science Alive coming up.
Thank you, Gerhard. Okay, just a quick shout out to all ASA members for some support for this event. Science Alive has a history with ASA that goes back 20 years. It is a public event that's actually run by a different group have actually bought the rights this year, and they're very keen for us to continue. It is a celebration of science from one point of view for the public, but also there's another phase to it. There's a STEM Careers Day, which is the Friday, where secondary school students are actually, they come in droves actually, with all things science. So there is a space zone in the Science Alive area. ASA has a community booth in the space zone. So that's what Science Alive is about. When is it? It's in August. The setup day is Thursday, the 6th of August. The STEM day is all day Friday, the 7th. And then there's public days on the Saturday and the Sunday. From a volume point of view, we would see 8,000 to 10,000 people a day. So what I'm looking for as coordinator is some very generous ASA members to provide a couple of hours at any time over that weekend to support our engagement of the public through our booth. Basically, ASA is part of the Science Zone, but we are unique. One, we're the only community group in that zone, and secondly, we're the only group that offers authentic experiences from the point of view of looking at the night sky, visual astronomy, astroastronomy, and we do actually set up telescopes with some images at the other end of the pavilion. It's just on the edge of the focal length of the telescope, so we can just get them in. But for literally hundreds of people each day, it's the first time they look through an eyepiece and they're looking at an image. As opposed to the real thing. And so it's about inspiring the young and the old. So we have people from 4-year-old to 94-year-old who stumble across our booth and are totally engaged. So we're looking for people to volunteer their time, whether it's a couple of hours on one day or you can spend a bit more time or multiple days. It'll be greatly appreciated. We do need to cater for that number of people, somewhere between 6 to 8 people a day, to ensure that we're not run off our feet, managing people with 3 telescopes and also the other kids' activities, as well as the astro imaging display that we have, takes a little bit of doing. You don't have to have any experience. You also don't have to be the world's best amateur astronomer. So in the last 2 or 3 years, we've had people who are new to the society, new to astronomy, but they have fitted in quite well because their experiences are from the beginning. And many of the questions we have from the public, and particularly from children, is about how do you get started? What does this thing do? How do you manage to do that? And so those beginning experiences for those people who think they might be inexperienced are actually really, really important. So if you're interested and able, please contact me. My email address is up there. I'll be putting out a general call to members for that support through ASA Chat in the next few days. Please don't be shy. One of the things that you need to be aware of, though, because we're working with children, you need to have a working with children clearance. And so if you've got a current one, fantastic. If you don't have one and you want to be involved, all you need to do is contact me and we'll get that sorted out pretty quickly. So it is ASA's biggest event from the point of view of having people come through for a potential first experience with observing the night sky and astronomy. So I hope to hear from you soon. Thank you.
Thank you, Michael. And I'll put in my own 2 words as a volunteer last year and in years gone by. It is great fun. Yes, there's a little bit of work involved, but it's great fun transmitting enthusiasm about science and astronomy to young people in particular. and some of the oldies who come along as well, who consider these things for the first time. So yes, please consider. It's great fun. Now, next month, we have an education session from Colin again on the electromagnetic spectrum. And our public meeting at 8 p.m. will be a display and a live cross to South Australia's largest privately owned and newest, certainly newest, may not be the largest, but certainly the newest and most capable telescope we have, given its sighting and its freshness, newness and capabilities. We'll have a live cross to see it demonstrated in action for slewing, hopefully the roof opening and things like that. So stay tuned for further news on next month's meeting with a live cross to this fantastic $1 million 30-inch telescope. We usually have merchandise at the back, not at this stage. Our merchandise managers are away presenting at a conference, so that's a placeholder for next month where there will be merchandise. Don't forget our sponsor, our main sponsor is Adelaide Optical in Gawler Place. Let them know you're an ASA member. Consider them when you're making your next astronomical purchase, and remind them that they give a discount to our members. ASA membership, for those who are not members, very reasonable, starting at $25 a year for students. Many benefits, which I've outlined so far, but also particularly member nights, out under the stars with people who know what they're doing. And yeah, it's a great way to learn the night sky as a beginner, and also follow your projects if you're a dedicated astro imager or observer. So you can see people there arrayed with red lights at our Stockport site, red lights being the most useful lighting for maintaining night vision. Members also benefit through our dark sky camps. Spending 5 nights at Alpana in the far northern Flinders Ranges is one of the highlights of my year. You can see the array of scopes there covered up during daytime in the campground. Similarly, Bendelby, slightly closer to Adelaide, with imaging members and visual members as well, and the array of telescopes around the campgrounds there in the lower photo. Social media, Facebook. We're on Facebook with announcements, Astronomy SA, YouTube, I've already mentioned, with a range of videos available, and other channels there. Thank you to all our helpers tonight. Of course, we're always interested in volunteers. We have as many needs to do things as potential volunteers out there, so please come and let us know if you're willing to help. Thank you for joining us this evening. Tea, coffee and supper available in the foyer. At this stage, I'll close this meeting and thank you all for coming.